Hello, everyone. My name is Scott Weaver, and it's a pleasure to be here today speaking with you about some of the interdisciplinary challenges we have in using climate science for engineering-based climate adaptation. Uh, I've recently founded a small independent consulting firm, Climet, that represents the first three letters of climate and the first three letters of meteorology. And that reflects our view that climate and meteorology, especially in the sciences, should be more strongly connected to each other. Up until this past summer, I was the executive director of meteorology at the White House Office of Science and Technology Policy. And I also list my affiliation prior to that as national director for windstorm impact reduction, because I think all of these experiences are highly relevant to the perspective that I approach this issue. If you had a different person talking to you with a slightly different background, you would get a completely different talk, even if we used all the same slides, because this is a very interdisciplinary issue. Today, I'm going to speak with you about some of the science and policy challenges we have. I'm actually going to talk a little bit more about the technical aspects of the science, but I'm going to keep it high level in the hopes that we have a broad audience here. And whenever we're speaking about interdisciplinarity, I think it's important that we try to keep it as high level as possible. There are many intra and inter-field challenges in climate science and engineering, including even between the climate scientists and meteorologists themselves. So we even have kind of some internal differences and challenges that we would need to overcome. Anyway, let's get right to it. So the bottom line up front, I'll try to give you the overview here. Essentially, I'm looking at this from the federal infrastructure side, right? The federal apparatus, and the policy programs and strategic objectives to make progress on this issue are in place, with respect to integrating climate science into engineering design. But in my opinion, they're poorly resourced and especially coordinated. So right now, it's basically there's progress being made. One thing I can cite is the NOAA ASCE partnership on this, but it's mostly a coalition of the willing. We do have a memorandum of understanding that has been signed between NOAA and ASCE. But as far as like boots on the ground trying to actually make this happen, it's very much a coalition of the willing currently, but it's gaining steam. There are official actions and committees and activities that are gaining steam. I still think we need more, but that's great to hear. And when you get into the science, progress is limited by a lot by the current level of scientific understanding. There are very different approaches in how we practice our craft between a climate scientist and an engineer. And I think some of those differences are things we need to get more comfortable with the way the other field conducts their science and their technology business. The one example of this I'll just give from within the meteorology and climate science world is, meteorology and climate science are highly probabilistic and very large scale. Like you hear things like, a hurricane category is a 1 minute sustained wind somewhere in the hurricane, right? It doesn't tell you where specifically, but they measured it somewhere. And this is just my view, but engineering practice is obviously more deterministic and localized. I've been in meetings and workshops where an engineer is telling me, I just need a number at X location. And to a climate scientist, they're not very comfortable with a number at a location like that, right? It's more about a PDF over a region. So there's some differences in approach that we definitely have challenges with. But let's just get right to the meat. I mean, I'm sure many of you have seen this. If you haven't, this is an extremely compelling graph. It shows how meteorological disaster impacts are increasing. There's a lot of information on this graph. I could speak with you for 10 or 20 minutes about it, which I'm not going to do. But the bottom line here is the bars represent the number of disasters that exceed $1 billion. Now, this is corrected for inflation. You can see the time series records from 1980 to 2021. That's what I have plotted here. And again, you can index the bars on the left. You could see the number of events on the left side. So you could just kind of move across and see how many $1 billion disasters there were in a given year. Obviously, you can see that there's an increasing trend, even when corrected for inflation. One of the interesting things is that the color coding gives you the type of disaster, whether it's severe storm or flooding or drought or wildfire, tropical cyclone, hurricane event. And so you could see that most of the increase in the billion-dollar events are coming because of what we call severe convection, severe storms. That's like tornadoes, thunderstorms, derechos, anything in that kind of bucket. That's driving the increase in the number of events that across this admittedly arbitrary threshold. And so that's driving the increase in that. But the costs are actually driven by tropical cyclones, and the costs here are indicated in the lines. Now you have several lines there, but if you just follow the red line, that's essentially the annual cost for that given year, that data point. And you could see if you look real closely that while there's much more interannual variability in the cost as opposed to number of events, you do see much more expensive years in the latter portion of the record. And we can actually split this record in half and count up some of the events and actually see what happened. And you could see that in the first half of the record, we had much less events. So it's not surprising to see that, you have triple the wildfire events in the more recent period. You have double the hurricane events, and it looks like more than quintuple the severe storm events. So really, really significant increases here. The other thing you'll note is that you can actually work through the costs if you look through the lines and actually tick off the major hurricane years, right? So like starting in 92, you could see Hurricane Andrew, that caused the spike there. In 2005, it was Katrina, right? In 2012, Sandy, I forgot 2008, that's Hurricane Ike. And then in 2017, you have the really large costs where you had the triumvirate of Harvey, Irma, and Maria causing significant damage. So you could see we have a serious problem here. So when we think of it, so we're thinking about disasters, some of that's related to climate change. Some of that is not related to climate change. And it's really difficult to tease those apart from a disaster metric. But we're talking about climate change here, and how do you respond to climate change? What are the three pillars of response? Well, one is what we call climate mitigation. In the climate world, mitigation means greenhouse gas reductions. In the disaster world, mitigation actually means adaptation in the climate world. Another discontinuity. But in any event, when we're talking about that, you see some keywords here. You hear about the Paris Agreement, things like clean energy or reforesting portions of land masses, net zero. You hear these kinds of buzzwords. So you have climate mitigation. That's one way to approach reducing the impacts from climate change. You have climate adaptation, which is what I'm going to talk primarily about today, but one small sliver of it. Climate adaptation is a very big umbrella. In the context of a lot of the things that I'll be talking about, you hear like resilience, you hear about design standards, building codes. Believe it or not, weather and seasonal to decadal forecasting is actually a climate adaptation strategy, right? Better forecasts will give more time to prepare. And climate model projections, which is something we're definitely going to talk about. And then there's this third response, which I'm not going to talk about at all, but I didn't want to leave it out, which is climate intervention. And there's a lot of conversations happening around this now. And you'll hear things like solar geoengineering, or carbon dioxide removal, carbon capture and storage, solar radiation management. That's a talk for another day. That's actually some very interesting science elements, policy elements, governance elements, equity elements really surround that, as they do all of these, but very interesting conversations happening in the climate intervention world. But we could say that for another day. We're going to focus on the adaptation side. So just a few weeks ago, the National Climate Assessment was released, and there's this really interesting quote in here. I am going to read it, which I usually don't like to do, but I will, because I think it's important. Despite an increase in adaptation actions across the country, current adaptation efforts and investments are insufficient to reduce today's climate-related risks and keep pace with future changes in the climate. That's really sobering. It's saying we're behind the curve significantly on adaptation. And it calls to accelerate current efforts and implement new ones, which I believe this is the topic I'm talking about today, is a new one, climate science for engineering design, that involve more fundamental shifts in systems and practices, can help address current risks and prepare for future impacts. And that's exactly what we're talking about today. And the graphic that is in there is also really astonishing. I mean, all I want you to take away from here is this is state-by-state actions on the mitigation side, so greenhouse gas reductions, and the adaptation side in green. And what you could see is, for the most part, there's been many more actions on the mitigation side. And this is very important. We need to reduce greenhouse gases to bring the global average temperature down. I get that. But as that quote says before, we need to really, really up our game on the climate adaptation side. It's very important because I don't think we're going to really be able to mitigate our way completely out of this problem, right? I don't think we're going to hit 1.5 or 2, or we're going to keep global warming to 1.5 or 2 degrees. It's more likely we're going to go way past there. And so the time is now. So when we get into this, we think about the policy. What are some of the recent examples of federal policy drivers connecting climate science and structural engineering design? This is one of the best programs you've probably never heard of, the National Windstorm Impact Reduction Program. I'm biased because I was its director for several years. But there's a strategic plan just sitting on the shelf, just waiting to be resourced, that has a lot of the elements that would go into efforts to connect climate science and engineering design. Not everything, but it'd be a really great start if we could do something with it. The Department of Commerce itself has included, they decided that they were going to have 5 primary actions in their climate adaptation plan. So they only choosing 5 things they want to make progress on. And one of those 5 was supporting the development of climate-ready infrastructure via the development of forward-looking building standards. So that's important at the department level, that's something they're interested in. And oh, by the way, NOAA and NIST are both part of the Department of Commerce, just so you know. Which leads me to this. This is language from a congressional federal funding bill. The annual funding bills they're supposed to pass every year. Sometimes they do, sometimes they don't, and they just continue along CRs until they pass it. Well, this is from a couple of years ago from when they passed. And basically it just says, look, we're concerned that building standards are designed with an assumption of stationarity, that the climate is stable, when in fact we know it's changing. And so we need to think about how we would work together. Engineers, this is a NIST-NOAA collaboration, but you could think about it broader. Engineers at NIST, climate scientists at NOAA, how they could work together to deal with this problem. And they're being told by Congress explicitly to do this. Okay, well, what about from the engineering side? Well, if you're an engineer, you know this. This is like, I don't know if it's true, but I call it the engineering Bible, because I've had the pleasure of being a climate scientist who has been sunken into a group of engineers for several years, and being privileged to be able to see how the engineering world works a little bit, coming from like an outside perspective. And I just know that this is always talked about, ASCE 7, because it has a lot of the design provisions for many of the hazards that we're concerned about in meteorology and climate science. And so the idea here is to figure out how to make aspects of the recommendations and the guidance that's provided in this, this every 6-year updated volume for the engineering community. How would we incorporate what we're learning from climate science into that? There are so that's like the technical document that practicing engineers would reference when they're thinking about designing. There are other manuals of practice, et cetera, but that's certainly one of the most important ones. And then there's, trying to think forward looking at this problem. And there are special projects that ASCE is supporting. For the first year or so that this project was stood up, I was the chair of Working Group 1, Climate Projection Models and Data. The results of this project, looking at life cycle performance, safety, reliability, and risk of structure and infrastructure systems, this will be coming out very, very soon. The final report on this project, it's imminent. I want to say within the next couple months. So let's jump into some of the science. So you probably heard global warming, right? The temperature's increasing. So here is the metric that we track global warming by. This is the globally average temperature. So it takes all the different data sources, observed data sources that we have across the entire world, and makes an average for the entire year. So you get one number per year. So it's a globally spatial average. It's also a temporal average for the whole year. Okay, so this is like the heartbeat of climate change, if you will, I guess, right? So you see a lot of wiggles in it. I mean, the first thing you see is that there's definitely a trend. I mean, this is why we're fairly confident that the world is obviously warming, and we know the mechanisms in place, and we know this is primarily related to greenhouse gas emissions. You see a lot of wiggles in there, right? Some years are higher than others, even along the trend. What you're seeing there is a manifestation of natural variability, which is internal to the climate system. It wobbles, it wiggles, it has natural occurring variability, and you see that on full display in the year-to-year variations. You also look really close, it's harder to see. There's kind of a 30-year multi-decadal signal underneath there. And if you were to run this through various filters, it would really come out. So we have different kinds of internal variability on different timescales. And that's the rub here. A lot of our problem is separating out the effects that has, not just on the global temperature, but on things that we actually experience. So this global temperature metric is really just a, it's a statistical artifact. It's an average over a very large area over a very long period of time. The interesting thing here is that it took 80 years for the first half a degree to rise, to go up a half a degree above pre-industrial levels. But it only took half that amount, 40 years, to go to the second degree. So it's accelerating. That's the point. But society doesn't actually feel the globally annually averaged temperature, right? That's not something your experience, can connect with. It's a tracking metric, essentially. It's a compact way for us to represent a bunch of different things, kind of like the stock market. It's like the S&P 500 represents all of these different, companies. And that's kind of what this metric is like. It's a gross, large scale metric, but it doesn't really tell us much about what we feel. Society feels things like this, and they feel it really in a serious way. This is back from 2013. This is the Bulletin of the American Meteorological Society, or what we refer to as BAMS. And the question they pose here is, can we forecast this 1 week in advance? Little side note, the interesting thing is, if you go in and read the article, it actually has nothing to do with disaster prediction. It has all to do with hurricane track and I think maybe intensity forecasting. But that's not enough. It's great to have a good track and intensity forecast. And I think a lot of times we can forecast those a week in advance in certain situations. But they weren't actually forecasted this. The article didn't have anything to do with the damage. And I thought that was kind of interesting, because it's coming from the meteorological community, we are pretty much, once our job is done, we're not really focused too much always focused too much on the outcome. I mean, certainly we do post-disaster work, but I don't know that we get into it as much as some of the engineering applications. And I think some more cross-pollination there would help us learn much more about disasters and how to connect them across, connect our knowledge across fields. So the idea is, really what we're trying to do is linking the globally average temperature, which isn't really a real physical thing in a sense, right? It's not something we feel, as I put it. How do we link changes in that to how disasters are changing or extreme events? Well, that requires something, it requires a lot of decisions. If I was an engineer, the first thing I would want to do is, you want to step back and say, okay, well, how do we link those two? But one of the first things I want to do is, well, what is that temperature metric going to look like in the future? And so this is one of the things we look at as climate scientists. So here's there's 4 different scenarios of the future. These are different scenarios based on how much greenhouse gases we're going to put in the atmosphere. So the red one, RCP 8.5, RCP stands for relative concentration pathway. There are actually newer ones. This slide is now old, as of, a few months or a year ago, but be that as it may, it's the general point is actually exactly the same as what's coming out brand new. But in any event, the high emission scenario is red, the lowest emission scenario is blue. And you'll see here, you heard these Paris goals, back in 2015, at COP21, you had the Paris Agreement, and it was, keep global warming to 2 degrees and really try for 1.5. And you could see, to do that, you would have to have a very low future emission scenario. Right. So these are the model projections. And you could see that not every model, there's dozens and dozens, I don't know how many, maybe even over 100 runs here, if you include all the different scenarios. And you see for each scenario, there's a variable, a range envelope. And as I mentioned before, that's how climate scientists are more comfortable. And you could see overlap between the different scenarios. And so the question becomes, we're most likely not going to hit any of these Paris goals. So if we don't, where are we going to go? And if I'm an engineer, I want to know, I want to be able to plan. So, we're going to have to pick some kind of number. I mean, what's the engineering design goal going to be? Is it going to be 3 degrees? Is it going to be 4 degrees? There's going to be trade-offs there. If you're designing for a 4-degree world, it's going to be more expensive than a 3-degree world. And so we really need to at least just have that initial conversation between climate scientists and engineers, like, where are we going to land on this, so that the engineers can at least focus on a given temperature goal, because the climate models are going to produce different kinds of weather events for different levels of global warming. Whether or not they're even right, they're going to produce, it's going to force differences in how weather is expressed if you have a much warmer as opposed to not so warm global temperature. Okay, so that's something that's called extreme event attribution. You're trying to attribute events to climate change. And here's another one of these graphics that I mentioned earlier with the disasters. Here's another graphic that I could speak with you for a very long time to describe why things are the way they are. But this is a graphic developed by climate scientists. Now, this is based on debate, argument, and conversations within the climate science community. Several top scientists, essentially, the national academies, developed a report and called them all in and got them to hammer out this graphic. And basically, what you need to know about this, there are two kinds of attribution. There's single event attribution, how much rainfall, how much extra rainfall did Hurricane Harvey has as a result of climate change that has already occurred? Because Hurricane Harvey would have occurred anyway. Most of these hurricanes would have happened irrespective of climate change, but are they more intense in some way? Winds, rain, whatever it may be. And so that's what single event attribution is. Attribution writ large is the grouping of events. In general, are hurricanes becoming more intense? Are they becoming more frequent? Those kinds of questions, the more overview questions, which actually are more relevant to engineering design, because you want to know what the PDF of the future is going to be, not necessarily what one event is. But one event studies can also help you understand the impacts you have in terms of disasters. I'll talk a little bit about that when I show an example later. But what you want to know from this graph is the further you are either up on the graph vertically or to the right, the more confidence we have in being able to attribute that style of event to climate change, whether it's writ large or single event. And so what you'll see here is this is actually not surprising that the temperature events that we have, the temperature events that are related to weather, heat waves, things like that, cold air outbursts or outbreaks, excuse me. It's not surprising that those are more tractable because it's temperature on temperature, right? We're talking about global warming, a global average temperature increase, and then we're talking about events that are related to that are also temperature. So there's no degrees of freedom in terms of the variable of interest. You could see, though, as things get more complicated, droughts are partially rainfall related and temperature related, as is extreme rainfall. But as you see, as events get smaller, as events get smaller in scale or more complicated, we have less confidence. Now, I want to point out that these axes, these events are relative to each other. So an event that's lying very low on the graph, it's not zero. It's not that we don't know anything about it. It's just relative to the other ones. That's what we know. And there's some really interesting characteristics that come out here. I could talk about each of these separately and give a explanation for why they are where they are, because it's really interesting how one's just a little further to the right than the other. But we don't have time, so I'm going to focus on tropical cyclones. And one thing you'll notice from tropical cyclones or hurricanes, this is tropical cyclones is the broader term for hurricanes that include tropical storms and hurricanes. Tropical cyclones are in a position where they are further to the right than they are vertically, right? So what that means is, in terms of climate science, we have more confidence in understanding how they're going to change as a group, like whether or not they'll become more intense or how is their frequency going to change. So, why is that? I think this is interesting to dive into. Well, tropical cyclones feed off warm water. You always hear this when there's a hurricane about to happen, right? You hear that, there's a hurricane. It's very warm out over the Atlantic, and this hurricane is going to take advantage of that and, become a category 4 or 5 or something like that. And when you look at the long-term trends in sea surface temperature or the hurricane's fuel, you see that there are positive trends globally, except for a very tiny spot off the coast of Greenland. So the ocean waters our temperatures are rising. So why is this important for hurricanes? If you look at all the hurricanes over history, if you will, over a long historical period, these are PDFs of the different strength categories of hurricanes as a function of ocean temperature. Now it's in Fahrenheit. But what I want to point you to, just look at the red distribution, right? That's for category 5s. Basically, what this is saying is that category 5s only happen when you're above about 82 degrees Fahrenheit. So you could see the relationship between an increasing temperature trend and our, the climate science community's, understanding that, hey, if this keeps happening, you're tilting the odds towards much more destructive hurricanes in the future. And we may already even be seeing some of that. I mean, of course, our experience says that. But we may be even seeing it start to emerge out of the data. It might take a little longer to really get a handle on that, but this is certainly consistent with the physics. So that's one reason why we have a better understanding of hurricanes in terms of writ large climate attribution. And then single event climate attribution would look at the event. How is this manifesting in terms of a given event? What I just showed, which is the warmer temperatures, how does that happen in an event? Well, you could look at the sea surface temperature anomaly. An anomaly is just a departure from the average. So you have an average state over many years. This is the departure, and the warm colors are warm sea surface temperatures. The blue colors are cold sea surface temperatures. And so this is pre-storm. You could see the northern Gulf of Mexico was very loaded. As you could say, it's primed, right? Hurricane Michael forms off the Yucatan Peninsula, moves through that area, and you can see the difference in the sea surface temperature from before and after. So the hurricane came through, it extracted all that potential energy, turned it into wind and rain, and deposited that along the coast big time. And there's the delta or the change. So you could see that change. So this is really important. So what does this have to do with design standards or anything, anything like that? Well, let's take a look out of the ASCE 7. This is out of 716. I know there's a newer one, so I apologize. These slides are just slightly old. All the new stuff is just coming out, and I haven't updated the talk yet, but basically the same idea. So what this shows is if you were to design a building or some kind of infrastructure system, here's the recommended, the recommended 3-second wind speed gust you should design your building to be able to withstand. So obviously, in South Florida, it's pretty high, right? You see in the Keys, it's like 180. Whereas, up in Tennessee, it's, 105, right? That makes sense because you don't get hurricanes in Tennessee. Now, in 2018, we had Hurricane Michael. One of the interesting things you'll notice, yes, it's 180 down here, but as you get up along the northern Florida, it actually dips down quite significantly to like the 130s, 120. I think there was one even here, if you really were to look at it, is like 115. And Hurricane Michael came right through this notch where the design wind speed is just much lower than it is either along the western half of the Gulf of Mexico or down into southern Florida. And that's because these design wind speeds are based off of historical data, and just not many strong hurricanes have hit that area for whatever reason. I can go into why there may be, what some of the reasons are, but it's really not important here. And Hurricane Michael was interesting because it shrugged off wind shear, which is detrimental to hurricane formation. Hurricanes don't like wind shear. It was able to kind of shrug that off and take advantage of those warm ocean temperatures and make landfall. There was another hurricane in 2019 called Dorian, which actually didn't make landfall, but was originally in the 4 or 5 day forecast was projected to make landfall, potentially as a Category 5, kind of near Cape Canaveral. That would have been another design level event if it shifted by 100 miles. So in some sense, I count it because it was right there. It just so happened that it turned at the last minute, thankfully. And then we had Hurricane Laura in 2020, which also was an above design level event. And so these events coming in, we're gonna look at them, the couple that are above design level. So these two are very different, but we're going to take a look at them, right? So let's take a look here. So Hurricane Michael. So this is a close-up of that area I showed in the box. Let's go back just so you can see. See, there's the box for Hurricane Michael, and that's the close-in area. And there's a lot of lines on this and everything, and it's not very easy to see everything. But what I want to point out is anywhere you see like pink and red is where the wind speeds were above design level based on engineering model and high resolution observations that were taken within the hurricane. Now, we don't have enough of those observations, so we do what we can. So this is kind of a combination of a model and meteorological observations, the ones that we can get. But pretty confident that large areas of Florida and even penetrating into southwestern Georgia, that's the border of Florida and Georgia. So it stayed above design level all the way in. This was because Hurricane Michael made landfall as a Category 5, so very large, very strong hurricane. Conversely, Hurricane Laura, also an above design level event, but initially wasn't. So the blues in this figure are just slightly below design level. So the reason why Laura was able to be above design level, yes, it made landfall over an area that has high design level wind speeds. So you would think, that would protect against a strong hurricane like Laura. But Laura was able to maintain its intensity long enough where the ASCE design standard gradient for the suggested wind speeds drops off rapidly, but Laura maintained its intensity. So that difference increased, and your above design level impacts don't start until you get much further inland. So kind of two different ways to look at this. But this is connecting this, what we're doing here is we're connecting this idea of anomalous climate environment, and now you're having above design level events. And yes, you can have anomalous climate environments without climate change, because remember, I showed you the climate system has these swings. But this is just something to look at when we start to think about writ large attribution and some of the impacts that is either having already or will have in the not too distant future. Let's take another really interesting look at wind. So these hurricanes occur over flat land, right? Like it's fairly flat there. It's no steep mountain ranges or anything like that. We take a look at Puerto Rico and Hurricane Maria. So the black line here that you see, that's the trajectory, the track of Hurricane Maria's center. Okay. And you could see if you were to treat Puerto Rico as a flat island, which it's not, but if you were to a first approximation, this is the estimated wind speeds you would get. This is very similar to these. It's just different shading, and it's actually a nicer and easier to see figure. But it's basically this without the, where it's above design level. But these are the wind contours of what we estimate in Hurricane Maria based on its trajectory and the pressure and all the parameters that we know about and some of the meteorological observations that we were able to salvage. But Puerto Rico is not a flat island. So you could see, estimated 140 mile, 130, 140 mile per hour winds. That's approaching design level, but it's not quite above. Okay. So the question is, all right, so Puerto Rico should have been good, but it wasn't. Well, why not? Puerto Rico has very steep topography. In a very short distance, you go from sea level, up to over 3,000 meters in, 10 miles, some places even less, right? Some places just a few miles. So very steep gradient. That has impacts on two very important parameters that occur within hurricanes: wind and rainfall. And we're gonna talk a little bit about the implications for both of those in kind of the last act of the talk here. So now I'll go back. Remember, this is what it looked like if it was flat. So we're going to superimpose that over the estimates that now will include the topography. And so if you include topography, that's what the shading is. So the lines here are the estimates you saw from the previous map, exactly the same ones. And the color coding are the wind speeds estimated when including topography. So if you go over here on the left, so you can see that in the flat version, you have wind speed here of 120. It slices right through a very dark red area that's shaded. Now, I don't know if anyone lives there, but this is just an example. That has got to be somewhere up around 200 miles per hour. So almost, more than 1.5 times, right? More than 1.5 times the wind that we would estimate using kind of the standard procedure to match with ASCE 7. But in reality, there are many areas that were above that, above that range. And then there are some areas on the west that are below it. So, but obviously the areas where the most damage occurred are the ones that we would see where you had the highest wind speed. So, understanding how climate is changing, how that relates to the different effects that occur on land when you have a landfalling hurricane based on it being forced to be different from climate change. But we also have to consider the smaller scale meteorological effects that aren't in climate models. A climate model wouldn't have helped you with this. You needed to get in on the ground, understand the topography, take some measurements, do some experiments with general wind and how it impacts topography, and come up with this more realistic version of the kinds of meteorological variables that Puerto Rico experienced. So wind is one thing. So what about rainfall? We don't talk much about rainfall. We think wind is the most destructive force in hurricanes, and to a large extent it is, and it drives the storm surge, et cetera. So that's a secondary effect. Storm surge is, arguably the most damaging effect, right? So wind, storm surge. We don't hear much about rainfall, always in the context of engineering, or at least in terms of the structural systems, which I understand it's not always a primary issue, but when you're thinking about disasters in a larger context, it certainly is, especially with respect to mortality. So, when I got into interfacing with the engineering community, because I was the director of the windstorm impact reduction program, it was wind, wind, wind. But we started to realize, we need to think about these things more holistically. If you're talking about the larger disaster research community, rainfall is certainly important, especially when we look at it in terms of mortality. So here's a really interesting figure. This is tropical cyclones. So this is hurricanes and tropical storms. All tropical cyclone mortality as a function of hazard from 1963 to 2012. And it's pie chart and shows you the percentage of fatalities based on the associated hazard in a hurricane. You can see storm surge has 49%. The original version of this research, when it was conducted, only did 1970 to 2000. That was the period they originally used. And the rainfall and storm surge numbers were almost flipped. That's because Hurricane Katrina had not occurred yet. So almost a large proportion of the fatalities in Hurricane Katrina, I think it was over 1,100, were from storm surge. So that, that really changed the look on this distribution. So I consider, because it's such an outlier of an event, the event happened, so you count it, but it's also a huge outlier. So it's unsure, we may need many more decades of data to kind of smooth this out. But the point I'm getting at is I look at the rainfall, the 27% mortality for rainfall as a lower bound, and that it's likely higher in reality, based on the fact that Katrina is such an outlier. And we know this from national climate assessments that extreme rainfall is increasing around the country. Now, this is mostly from non-tropical sources, but certainly some of this is from tropical sources, and that would explain a lot of why rainfall is becoming more extreme in the East in general than in the West. But we know that this is something that's occurring not just in hurricanes, but everywhere, that the rainfall is increasing. So I want to jump in and give you an example now. We were talking about tropical cyclones, and it was very low on that graph in terms of single event attribution. We have much less confidence back in 2016, but there's a lot of new research that's emerging. We're getting better at this, at being able to attribute and model storms in a climate changed environment versus what they would have been like in the pre-industrial. So here's a modeled version, a simulation of Hurricane Maria in our current climate, and it gives you the rainfall rate. And the numbers don't matter too much for our purposes here. Of course, they matter a lot, actually, but what I want to show you is mostly the change. So you model it in the current climate, and then you model it in a climate before we started really emitting lots of greenhouse gases, right? What we call the pre-industrial climate. And you take the difference. So if you take the current minus pre-industrial, what that's saying is, essentially based on the simulation, this is the amount of rainfall that has, or the extra rainfall or not, right? So some of the beiges are actually less rainfall, but they're outside the main circulation, except for this little blob here. But in any event, you could see that on that right quadrant, that upper right quadrant, there's already been an increase in the rainfall intensity from climate change that's already occurred. So this is already baked in. So that's interesting. And if we keep going and do a future high-level greenhouse gas scenario, this is for a high-level scenario, and we subtract the current climate, that's where we're headed for intensity changes in the future. So if this hurricane had occurred, let's say, I don't know, 80 years from now, if Hurricane Maria occurred 80 years from now, we'd be looking at that much of an increase, and that's quite a bit of rain, right? That's that's upwards of over a half an inch per hour increase in the regular rain rate. So that's a lot. That's a lot of rain. In any event, so we can do these interesting studies. The question here becomes, okay, let's pretend for our purposes here, this was perfectly accurate. Like this was actually a 100% perfect representation of Hurricane Maria, which it's not. It's pretty close though. I mean, actually, if you look at the left panel, the highest rainfall in Hurricane Maria occurred in that area, right? It may not have occurred with this exact pattern. It was probably messier and not as smooth, but they did a pretty good job here. But the question I have is, we still have issues in measuring meteorological parameters in extreme events, especially extreme rainfall. So, especially that. I mean, it's one of the hardest things to measure because some of our instrumentation gets affected in the storm itself, and satellites can't always see the most extreme rainfall and really be able, because they back out a calculation on what the rain rate is based on temperature, thermal emission, and other ways to see things. They don't actually record the rainfall like a rain gauge would, or see the rainfall even like a radar would. So one of the issues is, if we were to pretend that this was a perfect simulation, and I wanted to ask the question, well, what rainfall amount does that actually mean? This is just a delta. This is just a change. So if I can measure the actual rainfall that occurred, I could say, well, we would be expecting this higher amount 80 years from now, or 50 or 80 years from now, if I was planning for infrastructure or other kinds of planning. The problem is, a lot of our observations, as I mentioned, are very, very difficult to see. It's very difficult for them to measure extreme rainfall. And so this is an hour by hour difference plot from two different federal government science agencies who measured Hurricane Maria's rainfall. I'm leaving their names out because I don't want, I'm not trying to say like this agency's measurement system is poor. They're different, and the expectations of them are different. But just to kind of highlight, if you get into the meat of the storm, these middle panels, right? These panels that are kind of in the middle, you could see that there are differences that are upwards of 150 millimeters. That's 6 inches per hour. So, you're depending which measurement system you use, you would get very different answers if you have a 6-inch difference per hour. I mean, 6 inches of rain is a lot of rain, and that's just in 1 hour. And that's the difference. That's not the measurement of the rain. That's the difference between the two measuring systems. So we also need to have better in situ or in situ is the wrong word, event-based meteorological measurements for extreme events and figure out how to make sure we're really recording what actually happened so that we can contextualize our climate attribution better. Remember, this is meaningless unless I know this to a better approximation is essentially what it's not meaningless, but if I really want to get quantitative and understand what I would need to plan for in the future, having these two types of information isn't going to help me because I don't have an accurate measurement of the event itself. I might even have a better the model might actually be better in this case. We see some of that with Hurricane Maria, that modeling it actually might give a better representation of precipitation than the actual observations. And so this is something that's desperately needed. And so, that really, that leads me to some recommendations. And honestly, I probably have 10 or 20 of them, but I just wanted to choose a few. And there, I know I talk mostly about science, but there's obviously policy that could come and help out here at the federal level, at least with getting programs aligned. Funding would be nice, and then using coordination mechanisms that are in place to figure out how to best to deploy that funding to improve this kind of cross-pollination of engineering and climate science. So here's some recommendations. I mean, one of the things that really gets me is that politically and policy-wise, we often think about weather and climate as different issues, and they're treated very separately. And to some extent, I understand why. In policy, and you need to compartmentalize things so that you could wrap your head around them and figure out what's the best way forward and how to fund it. Like I get that, and the policy process is hard, and I don't. I'm not trying to take shots at the politicals or the policy process. It's a tough process. It's hard to figure these things out sometimes. Scientifically, weather and climate are not different. They're really part of a spectrum. They're part of the same thing. Two sides of the same coin kind of thing. And I think that's really important. I think we really need to start leveraging. From the outside, people would think meteorology and climate science are very similar, and they are, but then they're not. And you're trained differently depending which fields you come up in. And I've had I'll call it a privilege, it's mostly by accident, to actually spend time in both. And it's really interesting to see the difference. One time on a paper review, I got told a 0.7 correlation was meaningless in like a 40-year data set. That was a weather person who was obviously reviewing the paper because they don't deal with long-term time series all that often. So it's kind of interesting when you see, by the way, a 0.7 correlation in climate is like astonishingly good. I mean, that's like 50% of the variance would be explained by the association between those two variables. But in any event, one of the big things, as I mentioned at the outset, is leveraging the National Windstorm Impact Reduction Program. There's a strategic plan sitting right there. It's a great plan with input from the broader community. It's sitting there. It has objectives and recommendations. It could be implemented. All we would need is some funding and congressional reauthorization for the program. Hopefully, some of these things would lead to increased our formal research collaborations between climate science and engineering communities. But honestly, there has to be an incentive for that. I believe the federal government and the agencies like NSF, NOAA, NIST, NASA, DOE, USGS, you can go on and on with the science agencies that deal with climate, weather, and disasters. But there's a way we could do that. And you could probably leverage that through a program like the National Windstorm Impact Reduction Program. That's just one suggestion. But we also need our coalition willing to just continue to strengthen those interdisciplinary connections. And I think, going through the professional societies is another way, right? Because we can get the people together in all our various workshops and conferences. And two, they can help, influence potentially, if it bubbles up high enough, they can help influence congressional priorities if we can get some traction on this a little bit more. And then one of the things, I showed you the figure of the attribution, right, where all the different events lie on the graph. I think we're ready to update that. There's been significant advances in research. That report came out in 2016, but if you think about it, it's really the state of the science from about 2010 to 2015. So I think we're basically a decade past the science that was in there. So maybe it's time to revisit that and see if there's been, and not necessarily redo the report, but maybe some kind of updates to reflect the advancements that have happened in the last decade or so. So that's all I have today. I really do appreciate you listening. And I'm always interested in continuing the conversation. So my email address is here. Please feel free to reach out if you want to chat about this, or if you're interested in some kind of other, further engagement on these topics or any other topics related to climate science, engineering, weather policy, etc. And thanks for your time today. Take care.